One plan for today is to talk about improper priors and Jeffrey's prior, and I will try to make clear why would someone want to make would like to entertain such kind of priors. Okay, we will at least continue thinking about our little example with Gaussian data with known variance. And remember, just to refresh your memory, that we are parameterizing in terms of the precision, which is one of the variants. And the reason for doing this is that the updating equations are a bit simpler, a bit easier to remember. So we have Gaussian data, known variance. We have Gaussian prior, and the posterior is Gaussian with updated mean and updated precision, and those are the parameters. The precision is the prior precision plus 10 times the precision, n times, sorry, the precision coming from the likelihood, and the posterior mean is a weighted average of the MLE, the maximum likelihood estimator, and the prior mean, and the weights are proportional to the corresponding precisions, right? So the higher the precision coming from either the prior will give more credence to the prior mean, or if it's higher the precision coming from the likelihood, it will be give a higher credence to the maximum likelihood estimator. Okay, and I mentioned, and we will show an example probably of this later today, that conjugate priors are those priors that will make the posterior be in the same family. So in this case, the prior is Gaussian and the posterior is Gaussian. So this is a conjugate prior for this data. And we tend to normally, in practice, try and use conjugate priors because of that, because practically they are simple to use. Okay. So what would happen if we wanted to convey as little information in our prior as we could? Okay. So information is related to variability. The greater the variability, the smaller the information, right? So if we want to have very small information in our prior, then we want to make P as small as possible or V as large as possible, right? So if that is the case, if P, do I have it here? Probably I don't. Yeah, I don't need to write it down. Yeah. So if P is very, very small, if P tends to 0, then the posterior precision will depend mainly or only on the data, and the posterior mean, this will be close to 0, will depend basically on the data only, right? So we would like to make P as small as possible. But if P tends to 0, then this prior does not exist, right? This prior becomes flatter and flatter and flatter and flatter until it converges to 0. And that is not a prior because it doesn't integrate to 1. And it's actually not greater than 0 anyway, right? But in any case, if we have either enough precision in the data or enough data points, we could act as if P was 0, and this distribution, a Gaussian with mean at the maximum likelihood estimator and variance sigma square over n, or precision n times lambda, will be a good approximation to the posterior, sorry, right? So in principle, if we have either very small information or a large sample, we don't even need to calculate the posterior parameters. We just need to calculate the sample mean, and we'll have a fully determined posterior. Okay? So what this probably takes us to is to think about what it means to be non-informative. What does it mean to have very, very little information? How can we build a prior that has as little information as possible, right? One way would be to make the variance as big as possible, but sometimes that cannot be done. So we can think about ways of characterizing being non-informative. So if you don't have information, say, about theta, a parameter that lives in the real line, what can you say about the probability of this parameter being in two regions of the same length? So if this is theta, and this is L1, and this is, sorry, and this is L1 plus D, and then you have L2 and L2 plus D. So this distance is the same. If you really do not know anything about theta, then probably you would say that the probability of theta being in this region should be the same, a priori at least, as the probability for theta to be in that region, right? You know nothing about theta, so you don't have any degree of certainty about it being in different regions, okay? So if you carry on thinking in the same way, a natural non-informative prior will be constant, right? A uniform prior. That could be a natural non-informative prior. Okay? So let's say for some constant k. Okay? But now, if theta indeed is defined or can take any value in the real line, then for this prior to be a probability distribution, the integral over the whole space should be 1, right? That is the definition of a probability distribution. But, oh, sorry, didn't mean to do that. But obviously that is not the case, okay? If you integrate any constant in between minus infinity and infinity, that integral does not converge. Therefore, that is not a real prior distribution. It is a function. It is a constant function. For any value of theta, it will give a constant value, but it is not a PDF. And the important thing about that is that if we want to use Bayes' theorem, we need pi of theta, the prior, to be a probability distribution. Otherwise, the theorem does not stand, right? But in practice, we can see that if this is Bayes' theorem in all its glory. So if we solve k for any k larger than 0 in Bayes' theorem, then we can factor it out. It will cancel out, and then we will have that the posterior distribution will be proportional to the likelihood, right? And this will be a PDF if and only if we can actually integrate this likelihood. Now, the important technical thing here is that this likelihood is integrated with respect to theta, right? We know that the integral with respect to x has to be 1, because that is a probability distribution for x. But it needs not to be, and indeed it usually is not, a probability distribution for theta, right? So if and only if this integral exists, we could use a flat prior, a constant prior, as a Bayesian function, prior function, it would be not a prior distribution. So if we think about this problem, we found, and we used that, that the sampling distribution of the MLE, of the maximum likelihood estimator of X bar, is Gaussian. We know that with mean theta and variance sigma square over n, right? And we proved that we can use this sampling distribution with Bayes' theorem to obtain the posterior distribution, right? So again, this sign means proportional to, right? So it's proportional to 1. It's a constant distribution. Cool. Can you see? Yeah, cool. So the posterior distribution will be just proportional to this sampling distribution, right? Now, in order to make it a probability distribution, I would need to integrate from minus infinity to infinity. So this will be f of x bar in this case. I would need to integrate that with respect to theta. I know that that is 1 with respect to x bar, because that is the sampling distribution. But clearly, if I integrate these with respect to theta, this integral is also 1, right? So what that means is that the posterior distribution is Gaussian. Now note what Bayes' theorem has done. It has swapped the role of theta and x bar, right? If you're a frequentist, you can do probabilistic statements about the data when the parameter is fixed. If you're a Bayesian, you can do probabilistic statements about the parameter for fixed data, okay? So probably that makes things a bit more clear, or less. Okay? So the key here is that we can actually prove that the integral of the likelihood with respect to the parameter is finite. And that will not necessarily be the case always. So every time you use or you see the use of a non-informative prior, of a flat prior in practice, you should always check that the posterior distribution is a proper distribution, okay? Because that is effectively breaking Bayes' theorem. It is used quite a lot in practice because of that, because it sometimes works, and because in quite a few cases, you get results from a Bayesian perspective that are, at least numerically, almost identical to those results that you will get with a frequentist perspective, right? If you calculate probability intervals for theta there, they will be very similar to the confidence intervals that you will get from the frequentist approach, right? So that is the main feature or the main characteristic that makes making inference with improper priors attractive in practice. But that's exactly one of the weak points, because we don't want that. So that is that. In some cases, there will be more than one flat prior that we can use. So choosing between non-informative priors will become an issue, because if we have different priors, we will get different posteriors. And if we're arguing that we are not putting any information in our priors, and we get different posteriors, then the argument kind of fails, right? So one example of that is here. Think about a Bernoulli distribution, right? So you have, if X is Bernoulli with parameter theta, f of x given theta is theta to the power of x, 1 minus theta to the power of 1 minus x. X can be either 0 or 1, and theta lives in 0, 1. Theta is a probability, right? So we have a trial that can be 1 or 0, and theta is a probability of obtaining 1, okay? In this case, if we define a flat prior, constant prior, in the parameter space now is bounded. So we can actually check, and it's very easy to check that this is a proper distribution, right? This is a uniform distribution in between 0 and 1, so that is a proper distribution. I can use that, and the posterior distribution that I get out of that prior will be proper no matter what, okay? So I could argue this is flat, so this is consistent with my argument about not assigning different probabilities to regions of the same length. So it seems like a good candidate for a non-informative prior for theta, okay? I know nothing about theta, and that's what I want to say with that prior. But now we know that we can parameterize, just like we did here in terms of the variance or the precision, we can parameterize any distribution in any way that is consistent, right? So for instance, we could be interested for some reason in theta squared instead of theta, right? We can just write theta squared there, phi there, and define it as theta squared. And that will be our parameter. That parameter still lives in 0, 1. So it's still, the parameter space is still bounded, okay? So I could use a flat prior there, and I will get another posterior. But the prior that I get from my uniform here, and I will do this here so you can refresh your memory on transformations of random variables. So I'm saying pi of theta is 1, is uniform for theta in 0, 1. And now I have phi equals to theta squared, and I want to find the distribution pi of phi, okay? So I just need to define theta in terms of phi, right? Take the derivative. Right? And that means that I can now calculate pi of phi, as pi of theta evaluated at phi, that is 1 times the absolute value of the Jacobian right? And that's what we have there, okay? If you plot this function here, looks something like, probably it will be better to write it here. Something like that, right? So when phi is close to 0, this function is very big. When phi is close to 1, this is close to 1/2. Okay? Point is that this clearly is not constant, right? These will assign larger probabilities to smaller values of phi. Okay? So what this means is that if you think that a flat prior is non-informative, it might be non-informative in theta, but it's definitely informative in a function of theta, right? So flat priors are usually not really non-informative. They're just flat in one parameterization. And that can be a problem if you want to do Bayesian inference in a non-subjective way. Yeah. And this is something that was an active field of research. It still is, very much less so, but it still is. But it was a very active area of research back in the 80s and 90s. And even before that, there were people trying to come up with ways of proposing priors that were non-informative. So that means priors for which we need not to do any elicitation. We just need the model, and out of that model, we come up with a prior that will have a small effect as possible in the posterior. Okay? There's a vast literature of that. It's very technical, but what I will talk about and present to you is one of the most common approaches, at least for parameters of one dimension, and this usually works well in those cases. Okay? And this is called Jeffreys' prior. Jeffreys was a physicist that was concerned with probability and actually was the first kind of objective Bayesian. Very smart chap, anyways. So Jeffreys proposed this method to come up with priors, again, that we don't need to elicit, and therefore there are automatic, non-informative priors that depend only on the likelihood, right? And in some sense, will have these invariance to transformations in the parameter. Okay, so that is the key. We want to have a method to come up with priors that will render the same posterior no matter how I parameterize the model. Okay, this is the key. And the way we calculate or that we derive this prior is relatively simple. Are you familiar with Fisher information? No? No one? Okay, fair enough. So, as the name implies, this is a measure of information in the data, right? And it has to be with, this is the second derivative of the likelihood of the model. So it's measuring the curvature of this likelihood, right? So if this curvature, if the likelihood is really peaked, that's a lot of information. If the likelihood is really flat, that's very small information. So that's the idea behind Fisher information. Okay? And it's relatively easy to derive. You need to take the log of the joint distribution, calculate the second derivative, and then take that expectation. And this is wrong. No, this is wrong in your notes. I will correct that. In your notes, that integral is with respect to theta, and it is not with respect to x. So I'll update that today, and you can download the updated version tomorrow or any other time. But then take the expectation of this second derivative of the log with respect to x. Okay? And one very useful property of Fisher information is that it is, if you have a random sample, then Fisher information is additive. So the Fisher information in a random sample of size n is n times the Fisher information in one observation, which kind of makes sense. If you have a random sample, the information that you get about the parameter in each new piece of sample, in each new sample point, should be the same on average. Okay? So let's try and see how this works in practice. You have an example there, which is in page 26. And I will try and work that example more or less in detail now. Okay? So if you can start reading the example in page 26, please. Yeah. So Jeffreys prior for exponential data. Okay? We have xi from an exponential distribution with parameter lambda, I believe we use here. Yep. Okay. And we have a random sample of size n. Okay? Now, this is the time for you to remember that if you don't know what does this mean, you can go to your notation and distributions, and you have the PDFs there, means, variances, and so on. Okay, I really recommend that you use it because these will be in the exam. So if you know how to use these, the exam will be a bit easier. Okay. First thing we need is a PDF, and probably you are all familiar with that. We need the parameter space, so that's all the reals, and the sample space, sorry, the positive reals as well. Okay. Now, the first thing we need to calculate the posterior, and Jeffreys prior is the likelihood. Okay. So first thing we need is likelihood. Okay. Are we all fine with that? Cool. So now we have a likelihood. We need a prior. Probably I'll do the conjugate prior in a second, but for the time being, let's try and find Jeffreys prior, okay? First thing I need to take is the log of the joint distribution, or the likelihood. right? And second thing, second derivative. Okay. Oh. Now I need to take the expectation of this second derivative for fixed lambda. This is a constant. There are no x's there, right? Okay. And now Jeffreys prior is the square root of this. I will use that j just to make sure that that is Jeffreys prior. It's proportional to the square root of lambda square, and that is proportional to lambda to the minus 1. Remember, this means that I can drop any term not involving the parameter here, right? Any questions so far? Give you a second or two to catch up. Okay? Yep. So now, the posterior distribution, again, I will use J just to make sure that I know that this is Jeffreys. For data X will be proportional to the likelihood that I already wrote there. Times the prior. Okay. Now I am almost done there. Remember in our previous example that with the Gaussian data, we completed the square and then realized that that exponential of the quadratic term in theta looked like a Gaussian. So if I integrated out things, I would just need to find the constant that would make that integrate to 1. Okay? So I will do the same here. If you look at your handouts on distributions, lambda here, you know, it's larger than 0. N is larger than 0. That's the sample size. S is larger than 0. S is the sum of the xi's. Each xi is larger than 0. The sum is larger than 0, right? So this looks like lambda to the a minus 1, right? Which is the main part of a gamma distribution. If you look at your notes, what I need to add to this, to multiply these by, to make it a PDF, would be that constant there. And that will make that a distribution, so I can do the same here. Therefore, it's not longer, so that will be S to the n gamma of n, and it is a gamma in lambda with parameters n and s. Okay? So this sort of manipulation will be something that we'll be doing constantly in the course. We will multiply the likelihood times the prior. We will shape things in such a way that what we are left with resembles a known distribution. If we manage to do that, then we can bypass the need of carrying out that integral, because we know from our distribution handout which is the constant that we need. Okay? Is that clear for everyone? Okay. So this is just half of the story. The other half of the story is what would happen if, instead of being interested or parameterizing the model in terms of lambda, the rate, I would be interested in, say, the mean of xi. Call that phi, for instance. So if I'm interested in phi instead of lambda, I can do exactly the same what I did. First thing is f of x I given phi right? Just reparametrizing the model, the likelihood. Yep. The log, second derivative, okay. So this first term is constant. There are no x's in there. Okay. S is the sum of the xi's. So the expectation of the sum is the sum of the expectations. So that is, I am missing A2. Sorry about that. So now I have the prior. And I can calculate the posterior distribution given x will be proportional to that. Okay. Now, again, if you look at your handouts, this is the central part, this is the important part, the kernel of an inverted gamma distribution. That means that if you transform what I already deleted, if you transform the posterior distribution coming from the Jeffreys prior, that was that, sorry, if you use probability calculus and transform this posterior distribution, you will get that one, right? So no matter whether you calculate Jeffreys prior with one parametrization or the other, the posterior distribution that you will get will be consistent on the probability calculus, okay? And that's one thing that we didn't get with flat priors. So what we say is that Jeffreys prior is invariant on the one-to-one transformations of the parameter. And that's one key requirement that you need if you want to have a truly non-informative prior, right? You want the information in the prior to be the same no matter the parameterization. Okay. Good. Yes. Are there any questions? No? Okay, we'll do some, well, you will do some exercises. So before letting you go, Alison here will be an upgrade for the next 3 weeks. So hopefully, if you have questions, you can hopefully email Alison. Obviously, she will lecture. She will be able to answer your questions much better than me. And I will be back in week 6. Okay. Just a reminder in that. So yeah, week 5, I believe, you have to submit the first exercise, the first assess exercise for undergrads, okay? So that means that you need to bring your exercise and give it to Alison by the end of the lecture on Friday, okay? Please do it. It counts 5% and they're easy and they will help, so do them, please. I'll see you, yes? Sorry again? Yeah, it's only for 364 and 464. Master students can do it, and you will get feedback, but it won't be assessed. Okay? Thank you.